last class we discussed Ohm's law, current in a conductor and some questions based on resistivity and resistance. Today we'll start with the how we deduce the Ohm's law. So first is deduction of Ohm's law. Okay, sometimes question is there that how the resistance is constant. Now all of you know that resistance is V by I. Okay, and it is what? Constant in any conductor. Now remember, in last class what we have done, I is what? NeAVD. You remember? Current in a conductor is what? NeAVD. What is N? Electron density. E, charge of electron. A, cross-sectional area. Vd, drift velocity. And then what is V? V is what? Electric field into distance, E into L. NEA. Remember what is Vd? Drift velocity. You remember that? E by m into tau. So can we replace it by E by m into tau? Now this E goes out, cancels. And what is resistance? M will go up. It will be ml upon Ne square A tau. So this is resistance. Ml upon Ne square tau, and it's a complete constant. So this is the actual expression. What is M here? Mass, L, length. You know that this was a conductor of length L and what? Cross-sectional area A. So this makes Ohm's law what? It makes it constant resistance. Now even we can write resistivity in this term. If I say what is resistivity of a conductor, so resistivity can be defined in this term, that resistivity of a conductor. Okay, so resistivity already we know what is R. R is rho L by A. So rho is what? RA by L. Now if I put R value here, what is the R value? ml upon Ne square A tau, and then it is A by L. A cancels out, LL cancels out, and finally what we get is that M upon Ne square what? Tau. So this is the relation. This is resistivity. Okay, and very interesting thing is that in earlier case resistance is inversely proportional to tau. This is relation. Even rho is inversely proportional to what? Tau. So this is how we say resistivity and resistance. Then there are some small concepts. Say one is what is conductance. We have heard resistance. Now conductance is denoted by G. It is the reciprocal of what? Can you tell me? Reciprocal of what? Resistance. If I ask you, G will be written as 1 upon R. What was R? ml upon Ne square A tau. So it becomes Ne square A tau by what? ml. So this is G. G is Ne square A tau by ml. And then this is directly proportional to tau. What will be the SI unit? Reverse of ohm. Ohm inverse or MHO. This is the unit of what? The conductance. Now if I ask you what is then conductivity? Okay, this is conductance, then there is conductivity. It is what? Sigma. It is the reciprocal of, now you can understand, it is the reciprocal of what? Reciprocal of resistivity. So sigma can be written as 1 by rho. And if I put the value of rho, what was rho? You know that it is m by Ne square tau. So it is m by Ne square tau. So you will write m by Ne square tau. So reciprocate, it comes Ne square tau by m. So this is sigma. NE square tau by M. Sometimes they can ask you 1 mark question on these things. So sigma is also directly proportional to tau. SI unit will be, this is 1 by rho, so it will be ohm inverse meter inverse. So this is SI unit of this. This is SI unit of this. So conductivity, conductance, resistivity, resistance. And then there is another important term that is very important, is actually current density. Now current density is very important. That is how you define current density. Now current density, it is defined as current per unit area. Per unit area of cross section of the conductor, and it is denoted by small j, and it's a vector quantity. That is very interesting. It's a vector quantity. Remember, only one vector quantity we have seen right now. Current is not a vector, it's a vector quantity. And then j will be what? I by a. If I put I value, what is I? NEAVD by a. A cancel out. J is NEVD. This is also a relation, very important. Sometime it will be in the vector form. J will be NEVD. VD is what? Drift velocity. E is charge. So this equation is very important, how you define it. And there may be a question sometime that prove J equal to what? Sigma E. This can be the question in the paper. Prove J is equal to sigma E. So what is J? What? NEVD. And then J, put the value of VD. VD is what? You remember E by M into tau. So J can be written as NE square tau by M into E. Now do you know this value is what? Sigma. So J is sigma E. And finally we can write J equal to sigma. This is the vector. So this is relation, very important. Okay. JNEVD, they can ask you 1 mark question based on this. Current density. Current is a vector quantity and current density is a vector quantity. Current is not a vector quantity, but this is the relation for J equal to NEVD and J equal to what? Sigma E. Okay. So now we'll discuss about the temperature dependence. That is very important, of resistivity and resistance. So there is a very important topic, temperature dependence of resistance and resistivity. How the temperature of resistance and resistivity changes when the temperature of a conductor is increased or decreased. If you increase the temperature, what will happen to the resistance of the wire? If you decrease the temperature, what will happen to the resistance of the wire and its resistivity also? So we will have a very important relation regarding this. Now I think all of you know, if there is a conductor, say of resistance R0 and temperature T1. Okay. After some time, if the temperature is increased, all of you know that its length increases. It is R and temperature too. Do you know linear expansion of class 11th? And this expression you will remember, I have explained it in 11th class. Wow. See here, R0 and R. Now, what is delta R? It is R minus R0. T2 is greater than T1. You have increased the temperature. Okay. So remember, delta R is directly proportional to R0 initial, and delta R is directly proportional to what? delta T. What is delta T? Is T2 minus T1. This is the increase in temperature. Then delta R is proportional to R naught delta T. If you remember, there will be a constant alpha. You remember linear expansion, it is just like that. So delta R is this, and what is alpha is delta R upon R naught delta T. So this is a very important quantity, and this is known as temperature coefficient. You remember in 11th it is what? Coefficient of linear expansion. This is temperature coefficient. So this will decide that how the behavior of the material is changing with the temperature. And then can I write delta R, alpha R naught delta T, and in place of delta R what you can write is R minus R naught alpha R naught delta T, and this will be finally R equal to R naught in bracket 1 plus alpha delta T. This relation you have written in class 11, and even you have done one numerical based on this, if you remember. The resistance increases with the temperature in case of conductor, and alpha is a temperature coefficient SI unit, though it is degree Celsius inverse or Kelvin inverse. So you will see that generally we use degree Celsius inverse. So these are the unit. This is the temperature dependence of resistance. And in the same way, if this is the resistance, got it or not, can we write for the resistivity? Yes, for resistivity I can write rho equal to same way rho naught 1 plus alpha delta T. This is rho, it is the final resistivity, and this is the initial resistivity, and alpha is the temperature coefficient. So this is temperature dependence. And you remember that in case of conductors, this is very important concept. If the temperature is increased, T is increased, do you know, resistance R increases and resistivity increases. This is very important. Wow, because R is inversely proportional to a tau and rho is inversely proportional to tau. We wrote it in earlier. So what happens? Tau decreases, relaxation time decreases as temperature increases. So the temperature we are going to increase, tau decreases, relaxation time will decrease, collision will be fast. So time will be, collision of electrons will be fast. So R and rho increases. This is a conceptual question. Got it? So this is how we are going to explain about this. And now there are some graph, temperature dependence of the resistivity. There are some very important graphs, and we are going to talk about those graphs. One is resistivity temperature graph. These graphs are important. They are asked in what? Board exam. So this is temperature and it is given in Kelvin, and this is resistivity, and it is ohm meter. And this is graph for what? Do you know? This is for conductors. Like we have example copper. Then another graph we have. These graphs are very important. And this is resistivity graph with the temperature, and it is for alloys. Like nichrome we have alloy. And this is like this. So we have high resistivity of nichrome as the function of absolute temperature, it increases. And then comes the semiconductor. These three graphs are given in the NCERT. This is for semiconductor. Again, it is in ohm meter and it is in Kelvin. And semiconductor has reverse nature. So that means if you increase temperature, resistivity is going to increase. This is for semiconductors. Like we say, silicon as a pure semiconductor. So these three graphs, temperature dependence, so these graphs are very important for the term of temperature dependence, that how the temperature changes and how resistance and resistivity changes with the temperature. As you increase the temperature, in case of conductors, what happens? Alpha is positive. If I say conductors, so for conductors, alpha is what? Positive. But it's for semiconductors, you see, and carbon resistors. Remember, this is the case where we say that for the semiconductors, alpha is what? Negative. So these are the questions related with what? These are the concepts related with the temperature dependence. Got it? And then we can see some numerical based on the temperature dependence, that how the temperature and the resistivity changes. Say there is one question, I am going to write it, and that is at what temperature would the resistance of a copper conductor be double its resistance at 0 degrees Celsius. And this is the first part, and second part is the conceptual one, that does this temperature hold for all copper conductors, Cu conductors, regardless of shape and size. This is the question. And then how we are going to solve it? Very simple. We know the relation, that what is the relation, and alpha is given. Alpha for copper is 3.9 into 10 to the power minus 3 degrees Celsius. What is alpha? Temperature. And then how you define delta R by, do you know, R naught delta T? This was alpha. So delta R is basically R2 minus R1 upon, and it is R1 delta T. Delta T is what? T2 minus T1. So what is R2? It has become twice, double. So 2, we can write 2 R naught. What is R1? R naught. Here we write what is R1, R naught. What is T2? It is T minus 0. So solve it out. It becomes 1 upon T. So alpha will be what? 1 upon T. So can we find out the temperature? Yes, 1 by alpha. So 1 by 3.9 into 10 to the power minus 3. Solve it out. You will get the value of T here, 256 degrees Celsius. So this is the answer. Very simple. Solve it out. And then at last question, second part, this is the first part. Second part says, what will be the effect? That does this temperature hold for all? Answer is very simple, that alpha does not depend on size and shape. Alpha will be same. Alpha is the related with the property, size and shape of the conductor. So remember, this is very important, that alpha does not depend on size and shape of the what? Conductor. So it will hold good for what? All copper conductors. So it's hold good for all copper conductors, for all Cu conductors. So this is a question based on the temperature dependence. And now resistance we'll talk about series and parallel. So series and parallel, we all know combination of resistances. So combination of resistances or resistors. The first one is series combination, and you have gone through it in class 10th and capacitor in 11th. Now series combination, you know that there are three resistors, say like this, and they are connected with a battery of potential difference, say V, and I think all of you know the current remains same in series. So it is R1, it is R2, it is R3. The potential is V1, it is V2, it is V3. Okay, so this is how we are going to start, and all of you know that in series R is what? R1 plus R2 plus what? R3. So what we write, we know that consider three resistors connected in series across a battery of potential difference V. So very simple. By Ohm's law, what say Ohm's law? I think all of you know Ohm's law says V is what? IR. Okay, so that means here R can be what? V by I. This is now. Now for resistors, all resistors we are going to check is what? If we see for all resistors, the net potential difference is V1 plus V2 plus V3. Okay, and what is V1? I think all of you know IR1. What is V2? IR2. And what is V3? IR3. So put in second. So when you put in second, you know that what you get is IR, IR1 plus IR2 plus IR3. And then finally, you know that I will come out, and it will be IR1 plus R2 plus R3. So I cancel out, and this relation is at the last R equal to R1 plus R2 plus R3. This is what? Series. So in this way, this is the series combination. Very easy to prove it. And in series, three things are there like they were in capacitor. In series, you know that in series combination, three things are there. In series combination of resistors, first, current is same. Second, voltage divides. Voltage is different in the resistance. And third is that net resistance is maximum. So this is very simple. And I am giving you an example that if there are three resistors like this, and say 2 ohm, 3 ohm and 5 ohm, and they are connected with a battery of say 10 volts. So can you find out the current? Yes. What will be the current? What is the net resistance? Are they in series? Yes. 2 plus 3 plus 5. So it is 10 ohm. What will be the current? I is V by R. So simply 10 by 10 is 1 volt. And can you find out V1, V2, V3? Yes, that also you can find out. Can you find out the potential difference across the resistor? Yes. What is V1? IR1. What is I? 1 into R1, 2. So it will be 2 volt. What is V2? IR2. What is I? 1. What is 2? 3. 3 volt. Good. And what is V3? It is IR3. So what is I? 1 into 5. 5 volt. So individually also you can find out the voltages like this, like this. Net current is what? 1 ampere. This is ampere. Remember, it's ampere. So I is V by R. This will be the way we can calculate the series combination of resistors, how we have calculated it. Okay, so got it. So today we discussed the temperature dependence on resistivity, what is current density, how we are going to apply the graph on its graphs and series combination. So just go through all these concepts and solve the assignments. Okay, and thank you. Regularly watch my videos.